The simplest class of organic compounds are known as the hydrocarbons. From the name we can see that this kind of compound can only contain carbon and hydrogen. Okay? Because they only contain carbon and hydrogens, they will also only contain carbon and carbon bonds or carbon and hydrogen bonds. Why not hydrogen and hydrogen bond? Well, because if hydrogen and hydrogen bond with each other, they can't bond with anything else, right? Therefore, you also must be a continuous chain of carbon with hydrogen sticking out. Because it's a continuous chain, it could be one long linear chain or various branching of chains, and there are so many of these molecules that we must come up with a more systematic way of naming them. The system that we're going to use is called the IUPAC system. Okay? And in the IUPAC system, one of the fundamental starting point is to know how long the continuous chain of carbon is. Based on the length of that carbon, you will have a certain name based from Greek prefixes and ending in the word ane. When you are a saturated hydrocarbon, your name will end in ane. Remember that saturated means that you only have single carbon-carbon bonds, no double carbon-carbon or triple carbon-carbon. Okay, so if you only have two carbon in your chain, you will call the prefix is eth, and the name is ethane. If you have three, the prefix is prop, and you will call it propane. If you have four, the prefix is bute, and you will call it butane. 5, the prefix for 5, you should know, right? Pent, so it's pentane. Starting from 5, it gets a little bit easier to remember because it is prefixes that you know already. 6 is hex, so it's hexane. 7 is hept, so it's heptane. 8, oct, octane. 9, nonane. 10, dec for decane. The reason why you already know these prefixes, for example, pent, the pentagon has 5 shapes, 5 sides. Hex, a hexagon has 6 sides. A hept, oct, and non, deca. You might know this even from your pop culture, right? What's our calendar based off of? What is the 7th month? If this is 7th, what is the 7th month in our calendar? Trick question. It's actually September, right? September used to be the 7th month. What's after September? What's after 7? Oct. October is the 8th month. What's after October? 9. No, right? That's for 9. November is the 9th month, and the 10th month used to be Dec. December used to be the 10th month. There were 2 extra months added, and they got added right in the middle. Trivia question is for you to look up what month got added in the middle. And therefore pushing these months also down. That becomes, September now becomes the 9th month instead of the 7th, and so on and so forth. Okay? So let's take a couple of these again and draw out what they mean. For example, if you have a pentane, right, that means you have 1, 2, 3, 4, 5 carbons connected in a row. And again, each carbon must have how many bonds? 4 bonds, right? So we must fill it in with the rest of hydrogens. Each one has enough hydrogens to make 4 bonds. So as you can see, when I drew the structure of this molecule, it gets a little bit tedious in drawing on those bonds, and it takes a while, right? So we can come up with a shortcut. This is called the expanded structure. It's good to have an expanded structure because you see all the bonds, but sometimes it becomes tedious. So we have other ways to represent this molecule. One way we can represent this molecule is called the condensed structure. In the condensed structure, we try to group all of the units of the carbons together, right? So for example, this unit has carbon and 3 hydrogens. So we call this, we can write this as CH3 on this side, or we can write the carbon here and then H3 here. Right, that's CH3. That CH3 is connected to this carbon. How many hydrogens does it have? 2, right? So we call this a CH2. Which is now connected to this carbon, which is another CH2, connected to this carbon, CH2, and lastly, this carbon is a CH3, right? So just erase that. This is called the condensed structure. Sometimes you can even condense this even further by writing, again, I'm going to write this time as CH3, connected to CH2, how many of them? 1, 2, 3, right? And you can put a parentheses around that and put 3 and end it with CH3. Either of these are acceptable for condensed structure. Now even that, the condensed structure, is not very convenient. We have a better way and a faster way of drawing these structures. And you will really appreciate this way when you have a really large molecule. So let's talk about the structure. It's called the skeletal structure. And in the skeletal structure, you basically ignore all the hydrogens. Hydrogens are everywhere, so we assume they are already there. So for example, if I wanted to draw the skeletal structure for methane, it looks like this. 1, 2, 3, 4, 5. In a skeletal structure, right, so this is called skeletal structure. Right? In a skeletal structure, every time when you make a line, at the end of each line segment is a carbon. So here's a carbon, I make a line segment, here's another carbon. I make another line segment, here's another carbon, line segment, carbon, carbon. Okay? And we draw it in a zigzag fashion to represent really its geometry. Remember that the central carbon right here was a tetrahedral shape, and in tetrahedral, it's best to represent it as a zigzag. Okay? Remember, so let me convince yourself why that is. So remember that in a tetrahedral shape, you have two bonds that are in the same plane, one that's coming out and one that's going away, right? So that's why we draw it in a zigzag fashion. All right, let's talk about where the hydrogens are. The hydrogens are assumed to be there, right? So if you are a line segment and then you are the terminal end, that means how many hydrogens do you have? Remember, you have only one bond to another carbon, and every carbon must have 4 bonds. So you must have 1, 2, 3 hydrogens are hidden there. How about this one? If you're in the middle, you have already one bond to carbon, another bond to carbon. How many bonds do you have left? 2, right? 1, 2. These are invisible hydrogens. But again, in a skeletal structure, we don't draw in the hydrogens. Same thing, how many hydrogens are invisible here? 1, 2, 1, 2, 1, 2, 3. So that's the skeletal structure, right? So we'll get more practice with that. Now let's move on a little bit, and maybe we'll come back to this. Let's move on to talking about a skeletal structure that maybe loops back onto itself. It's not linear anymore, but if it loops back to itself, it makes a cyclic compound, like a ring, right? When you have alkanes that make a ring, meaning that the carbons that are usually in a straight line now loops back and reconnect with itself, what you have now is something called a cycloalkane. So for example, you see the 3-membered ring here. This one is a 4-membered ring. This one is a 5-membered ring, and this one is a 6-membered ring. All of these are under the class that's called cycloalkanes or cyclic hydrocarbons. So let's go back and take a look one at a time. If you have a 3-membered ring like this, you can represent it with the condensed structure formulas, with each one being a CH2 at each corner. So the skeletal formula is basically a triangle, right? So if it's a 3-membered ring, it has 3 carbons, the root word would be propane, right? But since it is a cyclic compound, we call this cyclopropane. Okay, so if you follow the same kind of pattern, you can name the rest of these guys. So this is a 4-membered ring. It has 4 carbon, each one having 2 hydrogens, so 4 CH2s. If you were to represent this skeletal formula only without any hydrogens in there, you would simply get a square. Okay, again, what's a name for something with 4 carbons? Butane. So this must be cyclobutane. Next, you got 5 cyclic here, so it's going to be cyclopentane. And lastly, if you have 6 carbon, again, 6 carbon is hexane, so this is cyclohexane.